Hi Wildcats. Today I want to talk about accuracy and precision. So we're still looking at how we make good observations when doing science, but we want to look specifically at accuracy and precision in making those measurements. So let's start by defining those terms. Accuracy is how close a measurement that you make is to the actual or correct value. So if an object is actually 3.15 meters in length and you measure it and you determine it's 3.19 meters, then you're pretty accurate, right? You're close to what the actual value is. Whereas if you measured it and it was 3.85 meters, well, now you're way off, right? And so this would not be an accurate measurement. So a good, you can see down here, I've got darts is a really good analogy for accuracy and precision. And so accurate is hitting what you're aiming for. So this diagram is accurate because we'll assume we're aiming for the bullseye, and many of these are close to the bullseye. So in this example, 3.15 meters is the bullseye. That's what the actual answer is, and 3.19 is pretty darn close to a bullseye. So that would be accurate. We often use accuracy and precision the same when we're just talking, but they mean different things. So precision is how close different measurements agree with each other. So here I've listed some numbers, some measurements, 3.16, 3.18, 3.15, and 3.18. This is precise because they are all close to each other. They agree with each other. You've precisely measured the same thing multiple times and gotten the same value. Not precise is when your values are all over the place. So if you measure something and the first time you get 3.16, the second time 3.17, 3.01, 3.34, your numbers are scattered all over the place. Your measurements are all over the place, and so you are not being very precise, or your measurements are not precise. And so here's an example of precision, but no accuracy, right? So this dartboard, the measurements are really close together, or you've hit really close together. So you are precise in your throws, but you are not accurate because we are aiming for the bullseye. So this would be precise because they're close together, but not accurate. This would be accurate, but you're kind of all over the place around your target. So you're accurate, but not precise. This is neither, right? We're aiming for the bullseye, and some get close, but some are really far, and they're not near each other. So this is neither accurate nor precise. And this, right, if you can hit the bullseye again and again and again, you are accurate and precise. Okay, so now that we know what those terms mean, let's talk about why we care about them, in particular precision. When we're making measurements, we need to communicate how precise our measurements are. And that's what significant figures do. Okay, so the number of significant figures that I write, the more precise I'm telling you that my measurement is. So if I write, for example, let's say 3, that is different in precision than 3.01742. This is telling someone that I've measured things out to the tens, hundredths, thousands, 10,000, right? Like to this many decimal places. I am super, super precise. I've measured it very, very carefully. Whereas this one is just 3. So the more sig figs I can use, or I use, the more precise it is. And this is where sometimes students run into problems because your calculator will give you like 3.0174289, and you just write down all the numbers. Well, you may not have actually measured it that precisely. And so let's look at this, two different rulers here, okay? We know when we get to use the number of sig figs, that every number we know for sure plus one guess or estimated value. So using this ruler, you can see they're graduated differently, right? They have different numbers of lines, these two. So what do we know for sure? Notice these candy canes are the same length. And so this one, I know that it is for sure 4. And then from there, that's it. That's all I know for sure. Now, is this 4.2? Maybe. Is it 4.3? That could be. I'm going to say it's 4.2. So this value right here, this is my estimated or guessing number. So this ruler and the measurements that are included on it, or the graduations, allow me to know for sure it's 4 plus one more number. And my guess is 2. But if you said 4.3, I don't think that you're wrong. We're not sure. This is our estimated value. Okay, so this is as precise as I can be. 4.2 centimeters is as precise as I can be with ruler A. Ruler B, on the other hand, is more graduated. So what do I know for sure? Well, I know for sure it is 4, and now it's less than 1, 2. I know it's for sure 2, so it's 4.2 for sure. I'm looking at these lines. Here's 1, here's 2. So it's more than 4.2, and now I'm guessing. So to me, it looks like it's about in between 4 or 2 and 3. So I'm going to say it's 4.25 centimeters. Okay, so this ruler is more precise because I can include more numbers. Now the 5 is my guessing value, right? It's my estimated value. So this one allows me to communicate more precision, 4.25. I know for sure it's 4.2, and I'm guessing it's another 5/100ths of a centimeter. This one, all I know is it's 4, and I'm guessing it's 4 2/10 of a centimeter. Okay, so these are different levels of precision because the rulers are graduated differently. So we need to be able to determine what counts as a significant figure and what's not. And so there are some rules associated with that. There's really 2 and a kind of. So the first rule, if it's not a 0, it always is significant. If you were writing a number like 4, this number, like 4.1, both of these numbers are communicating a level of precision, the 4 and the 1, because they are non-zero. Okay? Zeros are a little trickier because sometimes they count. So if you have there's 3 types: trailing, leading, and captive. Okay, so let's start. Trailing are decimals, are zeros at the end, right? They trail the number. So they're at the end, and they only count if the number is written as a decimal. So for example, 400, these zeros do not count because there's not a decimal here. So how many sig figs are in this value? 1. Okay, this is 1. Now if I wrote 400.1, now these zeros aren't trailing anymore. They are captive zeros. So they're in between. Right? In between 2 non-zero numbers, because 4 and 1 are non-zero numbers. So that means this has 4 sig figs because captive zeros always count. So here's the difference. These zeros, what are these zeros doing? These zeros are just telling me how big this value is. They're not telling me anything about the precision. They're just telling me that it's 400. Okay? It's different. If I wrote 40, I've got a different number of zeros. If I leave one off, now this is still 1 sig fig. These zeros are just telling me how big it is. So this is 40 instead of 400. So these zeros don't communicate anything about precision. They just communicate the size of the number. The same is true with leading zeros. So leading zeros are zeros that are in front of a non-zero number. So these never count because they're doing the same thing, just in opposite order. So the difference between this, right, 0.00004, this is a really small number. The difference between that and this is not the level of precision, it's just these writing fewer zeros is telling me how small it is. So just like in 400, these zeros at the end tell me how big it is, these zeros in the front tell me how small it is. And so those never count. The only time zeros count is when they're telling us how precise a number is. And so in this case, this really, really small number that they show, 0.000400030001, these zeros at the end are telling me I've measured it, that it's this small, 0.00004, and then I've got more precise, 0.003. 000. These numbers are telling me how precise it is. I've measured this out to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal places. 12 decimal places. So I'm using like the world's most precise measuring tool here to get to this level of precision. That would be different than if I dropped this 0. Now this is telling me a different level of precision, right? This is saying this is my guess number. And so this is how precise I can be. If I drop that 0, now this is how precise I can be. So those zeros at the end count if it's a decimal. If there's no decimal, they don't count because it's just telling me the size of the number. So in general, if it's captive or in between 2 non-zeros, it doesn't count, or it does count. If it's at the end, it counts only if there's a decimal, and if they're in the front, they never count. Okay, so in class, we're always going to do things to 3 sig figs. It's just going to make our lives easier. And I get ahead of myself. Let's practice this one more time. Okay, so these rulers are different levels of graduation. And so here, what do I know about this one? Let's make a measurement. Okay, so you look at this picture, think about it, maybe pause the video. What do you know? You know it is, well, I know it's 3. 1, 2, 3, 4, 5. I know it's 3.5 for sure, and then that's it. It's definitely not 3.6. So now I'm going to make my guess number. 3.5, I'll say 8. Okay, so I've got 1, 2, 3 sig figs in here. This ruler, on the other hand, what do I know? I know for sure it's 3. And that's it. And then, I mean, let's see, is that exactly in the middle? To my eyes, it is. So I would say this is 3.5. This is my guess number. So this ruler is less precise. And I can get that, I understand that just by looking at these two numbers, because this one has 3 sig figs and this one only has 2. Alright, so easy way to get around sig figs is to use scientific notation. Scientific notation is this format a times 10 to the some exponent. And I know sometimes students hate these because they forget the rules, but we're going to review these. Okay? Scientific notation just makes it easier to write numbers that are really big or really small. And that's what we're doing by using this power of 10. So for example, I could write 4.31 times 10 to the second. So this is 3 sig figs, right? 1, 2, 3. Always, and we'll always use 3 sig figs. So putting things in scientific notation is an easy way to always have the right number of sig figs. Now, this number written in non-scientific notation would just be 431. So 431 is not that big of a number. Now 43100000000, I'm going to get tired of writing that. And so it's just often easier to write things in scientific notation. So let's talk about how to do that. Okay, so we've got some steps here. First, find the decimal. Okay, so I've got a number here, a big number, and since the decimal is not written, we know from math class it's at the end. Okay, so find the decimal and move it to the left or right until you reach the last non-zero digit. So ready? 1, I'm moving it left. 2, 3, 4, 5, 6, 7, 8, 9. So now, boom, I've reached my last non-zero number. This is a non-zero number. Okay, so now I'm going to write this as 2 point. Okay, count how many places I moved the decimal. Okay, so I moved it 9, right? I said I had to move this 9 times, and that's the b. That's the exponent. So I'm going to write 3 sig figs. 2.0. Now this 0 is captive, so it counts, and then this is where I stop. So this 6 means I have to round the 3 up to a 4. Right? Rounding rules, 5 or more, round up. Okay, so this is 2.04 times 10 to the 9th. And now sometimes students say, well, I get confused if it's positive or negative. If you move the decimal left, it's positive. If you move the decimal right, it's negative. Okay. So these are the same numbers, but I've written this with 3 sig figs, and this is the exponent version of it. Okay, so hopefully that helped. We are looking at making observations comparable, and one way we do that is by not only being accurate, but also being precise in our measurements. And we saw that sig figs are used to communicate precision, and that we can estimate or communicate where we estimated, right? The last digit is the estimation one. And then we saw that there are rules for determining sig figs, as well as then putting them into scientific notation.